Hello class, welcome to the next chapter in our textbook. This is called Frequency Response. It's chapter 9. So the material on frequency response is important, and so we figured that I would at least do some lessons and put them up on BabyLearn for you to listen to and read through the PPT on your own time. So this is just some extra material for you this semester, but I think this course 380 is not complete without doing at least a little bit out of this chapter, um, and hence we are doing this for your, I guess, benefit. Okay, so I will only take 1 week, which would normally be 2 days in the week for you if you are sitting in class. So I have for day one, actually let me show you the contents, which is the next slide, where you can see all the topics in this chapter, and I'll show you what we are covering. So as you can see, there are 10 topics in this chapter, and obviously this is a long chapter, so it would have normally taken me at least 2 weeks to go through all of this. So since we don't have so much time, I thought we would at least do the first 4. So there's an introduction, and then low frequency response of the basic common source and common emitter amplifiers. And then we have the high frequency response of the common source and common emitter amplifier. In between, there is one topic which is important. It talks about the internal capacitive effects at the high frequency of the MOSFET and the BJT. So bottom line is there are 4 topics we'll cover, and the remaining hopefully you'll see at some other point in your studies. Of these, the first 2 topics will be the subject of my recording now, the theory of it. So that will take about 45 minutes. The next recording will be some problems only on this. It's another 45 minutes. Then, for day 2, I'll cover the theory of this 9.2 and 9.3 and the problems on 9.2 and 9.3. Okay, so that is just the minimum amount of information I think you require to say that you've finished the course. Otherwise, there would be a little bit of a gap in your understanding, and you will struggle later when you have to do more advanced courses. All right. Okay, with that, let's move on to the introduction. So the introduction, here I will review some of the material that we have already studied. In fact, a lot of this will be material we have studied, mostly in EE 280, where we had a chapter on frequency response, and then we had a chapter on filter circuits, if you remember low pass, high pass filters. So this is kind of a review of that material, because this is required for you to understand, the other material, later material in chapter 9. So the first 15 minutes of what I'm going to talk about, the remaining time, will be devoted to just a refreshing of your memory of frequency response and filters. Then we'll actually jump into mostly into 9.1, which is a low frequency part of the frequency response. All right. So by now you probably are familiar with this kind of circuit and graph. So this, you may remember, is the example of a high pass RC circuit. Similarly, this is a low pass RC circuit. I hope these figures and this graph reminds you of what that is. So in the graph, we have a curved portion, the blue portion, and then we have two lines which um, are also related to frequency response. So frequency is on this axis and gain is on this axis, right? So for a simple RC circuit like this, the voltage is the source voltage shown here, and that's the input voltage, and the output voltage comes out of the resistance here, or it's taken out of the capacitance here, right? If you consider this as a series circuit, you have kind of a voltage divider. So the maximum voltage out will be less than the voltage in, obviously, both cases. So VO by V in, or V out by V in, has a maximum value of 1, and if you take the decibel of that gain, which is V out by V in, the maximum you'll see is 0, right? Because uh, log of 0 is 1. So in this kind of circuit, which we have studied a lot, there's not much, nothing happens above the 0 dB line, because that's the maximum gain you can expect in a circuit. Not really gain, it's more of a voltage division. But anyway, this side, the y-axis is always called gain, and it shows in dB. You probably also remember the minus 3 dB point, right? On this blue graph, which is the actual value of how the output voltage by input voltage, the ratio drops with respect to frequency. At 0 hertz or 0 frequency, this is an open circuit, right? So no voltage appears at the output, that's why you see 0. On the other hand, here, if this is an open circuit, then all this voltage just appears here, and that's why you see that the output at low frequency is 1 or 0 dB. On the other hand, at a very high frequency, this is a short circuit, right? So current starts to flow, and the voltage across this point, if it's a short circuit, approaches 0, right? So at very high frequency, you see the output voltage drop off, and hence the graph looks like this. Now, in a chapter on frequency response, we were introduced to the idea of the Bode plot, right? The BODE, Bode approximation. So what the Bode plot helps us to do is, at a certain frequency called the break frequency, we create two straight lines, right? One horizontal and another one at a certain slope. What is the slope? That slope we know is minus 20 or 20 dB per decade. That means if you plot this as a logarithmic scale, and if this point is 10 times this point, right? This point is 10p, this is p. So over a travel of uh, 10, a 10 multiplier of the frequency, the decibel value falls by 20. So you can see that it falls to minus 20 if it was 0 here, right? That's why we call the slope of this line 20 decibel per decade slope. In this case, it's falling minus 20 dB per decade. In this case, it's rising plus 20 dB by decade. So all these ideas, I think, are quite familiar by now. They should be. Otherwise, I haven't done a good job teaching some of this to you. So please go back and look at some of the material from the past. All right. Then we had some exposure to this concept of frequency response, right? Now here you will notice that we are not at 0 dB anymore. We are at a high value of dB, which is 40 dB. So this is not a simple, voltage divider like this, but this frequency response is for a circuit where amplification is happening, right? So if you think it's a voltage amplifier, then the voltage amplification is not just 1 or less, it is some definite numbers, right? 10, 20, and so on. So in the future, you will see more graphs like this, where on this axis you have certain positive values of dB, not just the 0 point or the 0 dB line or as the flat portion. It can be some other high value depending on how much amplification is being achieved in the filter circuit. But still, many of the other ideas are still applicable. So for example, the minus 3 dB, right? We talked about the minus 3 dB line here, but this was minus 3 dB from 0, so we were at minus 3 dB. But here, if we are minus 3 dB from 40, we are talking about 37 dB, right? So this is minus 3, but with respect to the mid-frequency flat region, which is 40. So I just want you to understand that now we are dealing with amplification of more than one with real amplifiers like op amps and just BJTs and FET amplifiers also. Again, we can define bandwidth, which is the difference between the high cutoff and the low cutoff, and these frequencies F1 and F2, they are called cutoff points or break frequencies. They have many names, but the region between the 2 points, on this side where it falls by minus 3 dB, this side where it falls by minus 3 dB, that portion is called the amplifier bandwidth. And this region, the flat region, is called the mid frequency. On this side is the low frequency, right? LF, this side, this portion. Similarly, HF is the high frequency. And so there is a low frequency cutoff point and there's a high frequency cutoff point. And F is, of course, the frequency. The bandwidth is F2 minus F1. So I found this kind of example somewhere. I thought I'd bring it in so we can both refresh our memories. Okay, now we have one graph here from the introduction portion of this chapter 9.0. So essentially he is telling you the same thing we just saw on the previous slide. But here the mid-band gain, we use the term A followed by M. Now remember, we have used AV and AO and GV and all that in the previous chapters. But for now, one important gain point is AM, and we assume that AM is available through a lot of range of the frequency band. So this portion is the mid band. Then similarly we have the low frequency band and the high frequency band, and on both sides we have the minus 3 dB point. Okay, so this gain on this side can be shown as 20 log of the absolute value of the gain, the voltage gain VO by V signal in dB. Okay, so this is the terminology from our textbook, so you're going to see quite a lot of it in this chapter. So there is a wide range. Sorry, let me expand this. Okay. So there is a wide frequency range over which the gain remains almost constant, which is here. Here, the capacitances in the circuit can be neglected. That means the impedance offered by the capacitance at these frequencies can be neglected because the impedance is so low, right? Now at lower frequencies, the magnitude of the amplifier gain falls off. This occurs because the coupling and bypass capacitors no longer have low impedance, their impedance is high. So anytime you have a high impedance, your signal cannot go through, right? It's facing resistance, so the magnitude of the signal starts to fall. So the gain starts to fall. So that explains what happens on the low end side. Now on the high end side, it's not the coupling capacitors and the bypass capacitors, but it's the capacitors inside the BJT and the FET. Not anything we bring in from the outside, but they just exist on the inside. Okay, so that is the reason for what happens on the high frequency side. So the gain of the amplifier falls off at the high frequency end. This is due to the internal capacitive effects in the BJT and in the MOSFET. So we'll study the low frequency portion separately and the high frequency portion separately in this chapter. The amplifier bandwidth for discrete amplifiers is defined by FL and FH. Okay. Now why do I say only discrete amplifiers? We'll talk about it in the next slide. Okay. So here we have some graphs where we show this looks slightly different from this, right? So this kind of graph is for discrete amplifiers, while for IC amplifiers, the big difference is a lot of the amplifier connectivity between stages in an IC is direct coupled. That means we try to avoid having capacitors because capacitors are difficult to make on an IC. So most of the stages, if there is a multiple stage, right? We talked about multi-stage amplifiers in the last chapter. So if you have 3 stages in an IC, they are connected to each other directly. So there really isn't any capacitor on the low end to create problems. So in theory, we can say that the low end frequency response goes all the way to 0 Hertz to DC in an IC amplifier. In a discrete amplifier, that's not possible. To connect stages to one another, we use coupling capacitors, and then also for biasing, we use resistors with bypass capacitors, right? In ICs, for biasing, we generally use current sources, so we don't have to worry about bypassing those using coupling capacitors or bypass capacitors. So the point then is, for discrete amplifiers, this low end falls off, while for IC amplifiers, you can assume that a flat frequency not only is in the mid band but also goes towards DC all the way to 0 Hertz. Okay? So that is one thing that is important to understand as the difference between IC amplifiers and discrete amplifiers. Because here we have a lot of capacitors, here we don't have so many capacitors. Here high frequency drop off does happen because we have so many devices, BJTs and MOSFETs packed into a closed space with both conducting terminals and non-conducting silicon oxide, right, insulation portion. So capacitance effects naturally come up in ICs also, and so this high frequency drop off cannot be avoided even with IC amplifiers. Alright, here's just one more example I found where you can see some real numbers. So for example, the mid-band gain AM is 100 volts per volt, which is 40 dB. Then for this particular amplifier, the 3 dB frequency happens at 0.1 megahertz, which is 100 kilohertz. So at this point, which is the break frequency, the gain reduces by 3 dB. So that means 40 minus 3 happens somewhere at this point, 37, right? Similarly, gain reduces to 1 at 10 megahertz, and this point where it drops to 0 absolute value, the ratio is 0, which is, sorry, it's 1, right? Uh, 0 is the dB value. So when it drops to 0 dB, that means the input or the output equals the input. There is virtually no gain or just gain of 1. So such a point is also important in a lot of the analysis, particularly of the high frequency side, and that point is called the unity gain frequency, or a gain of 1. And this happens for this amplifier at 10 megahertz. So you can see from 0 to 100 kilohertz, it's pretty much a nice flat value, but after 100 kilohertz, it starts falling, and by 10 megahertz, it's come down to 0. So you can't really trust the amplifier too much here, but you can trust it definitely here. Okay, so that was another introduction. So let me quickly go through some old material. Hopefully, this won't take too long. Okay, so we have an RC circuit, and it has a signal and an R and a C, and the output is coming out of the capacitance here. So we write the the output by input, which is the transfer function, as this impedance divided by the total impedance, right? So if you wrote the voltage divider formula, you know that the voltage here would be the input voltage times this impedance by the sum impedance, right? So you know the voltage divider formula. So based on that, you can create V0 by Vs, also called the transfer function, and write it in this form, right? Now, here you see the term RC, which we know is an important property of this circuit. So RC is also known as tau, the time constant. But if you took the reverse of 1 by, which is 1 by tau or 1 by RC, you come up with a frequency in radians per second, and that frequency is a natural property of this circuit, and it's called the minus 3 dB frequency. So what we notice is, at this frequency, the the gain drops to minus 3 dB, right? And this term, the transfer function term, we like to write it not in terms of just RC, but in terms of the omega 0, which is the 3 dB frequency. So this stuff also, I think you'll remember having seen this before. So continuing a little more just on this. So if you write this in this form, as I just showed you, then you multiply and divide by this. This is just one more step. You can come up with the HW as a complex number in rectangular form. That means this is like x plus jy, right? There is a j, there's an x and a y. Also, you can write the same thing in terms of in a polar form, which is h magnitude and angle phi. So the magnitude is this, and the phi, the phase angle, is this. You see that at any frequency, omega 0, you know, it's just a constant, it's RC, right? So the response at any frequency omega can be written either in polar form or in rectangular form. This form, of course, is most important, and you must be, comfortable with this. So now if you take this polar form and you plot it, there can be two types of plots, right? There can be an amplitude plot and there can be a phase angle plot, right? So as the frequency increases, gain falls to 0. So here in the table you'll see at 0 frequency, then at frequency of omega equals omega 0, which is just 1 by RC, and then as the frequency goes higher, you notice that H falls from 1 to 0. That means this at this point the gain is 1, and at this point the gain is 0. What happens to the phase angle? When the gain is 1, the phase angle is 0. That means the output is in phase with the input. But as the frequency increases, the phase totally goes to minus 90. So that's what you see here as going from 0 to minus 90. So both the frequency plot and the phase angle plot are important when we are studying the effect of frequency on a circuit and the circuit's gain. Okay, so the cutoff frequency, right, or break frequency, we've talked about this quite a bit, omega C or also omega O as it's sometimes shown. What happens at that point? The gain drops to 0.707, which is 1 by root 2. That 0.707, if you take the log of it, is minus 3 dB. So remember, at the cutoff or break frequency, the gain drops from a high to 0.707, or if it is rising, then it rises to 70% of the highest possible. Okay, all right. So you can write in terms of power. If this is a power equation, then it's P max by 2. So this point is a half point. But if we are only talking about voltage or current, because power has a square function, voltage or current doesn't have a square, hence the root 2. So 1 by root 2 is 0.707, which is this point. In terms of decibel gain, this 0.707 is 3 dB, and the maximum that's possible is when V out equals V in, or this ratio is 1, and that is shown as the 0 dB. So everything is 0 dB or lower, right? Now, let me also introduce you to low pass and high pass. Low pass means the amplifier or the circuit allows everything lower than the cutoff frequency to come through without any change, right? The gain is 1. The high pass, the gain is 0. Sorry, high pass, the gain is the opposite. Everything above the cutoff frequency is allowed to go through, and everything below, in theory, is doesn't have enough amplification, and so we should not consider what is happening below the cutoff in a high pass to be useful. So we say that the circuit is only useful for values above the cutoff frequency. So low pass, all the frequencies below the cutoff are useful, meaning the circuit can work with those frequencies, but anything above it screws up, it destroys. Similarly, high pass, anything higher than the cutoff frequency, the circuit can work with it and allow it to go smoothly, but anything lower than that, it destroys. Okay. So there is more high pass, low pass. I don't have too much time to go through all this, but the one thing I want to point out is, and of course we are only dealing with RC, so you can ignore the RL business here. Remember, the transfer frequency looks like this for a low pass circuit, where you have the omega on top and a bottom denominator is S plus omega, and of course omega C, the cutoff frequency, is 1 by RC. Similarly, in a high pass filter, notice that there is an S on top and an S on bottom. Numerator and denominator has an S, and remember this form of the transfer function, and the omega SC is still 1 by RC. It just depends where you take the output from. Now a little more on Bode plots. We've already introduced you to it, but if you remember this chapter, if you have a very simple transfer function with one pole, you remember the pole is the bottom and the zeros are the top. So the factor in the bottom is s plus 1. That means it has a corner frequency of omega equals 1. This can be sometimes given as s plus a, which means the corner frequency is a radians per second. So we draw the Bode plot like this, right? The actual curve is like this, but with a board we put two straight lines and the slope is minus 20 dB per decade. So you've seen this. This is the frequency. Luckily in this chapter we don't deal too much with phase shift. Mostly we deal with the magnitude plot only. So here's another example of if you have a low pass filter. Here is a corner frequency, here's a unity gain dB, and how the Bode plot is drawn as shown in red. Okay, I don't have time to go through too much of this because we have to cover new material. I will let you look through this. For a complex function, right, where we have many one pole and one zero, how to build a Bode plot. It consists of different sections. So that was something we studied. Here's one last slide on the stuff we have studied in the past. There are two poles here at 0, another pole at 10, minus 10, and then we have a 0. So if you have a complex transfer function like this is how you create the net Bode plot and how your frequency changes or how your gain changes with respect to frequency is shown by this kind of a plot, which is created by adding the effect of each of the poles and the zeros. Okay, so that was the review. From now on, what we study is fresh stuff as related to our amplifier circuits, which are our BJT and MOSFET circuits. So chapter 9.1 or section 9.1, low frequency response of the CS and CE amplifier. So here we have a CS amplifier. Sorry, okay, it's not going anywhere. Put it here. And we have three capacitors. Now this is a discrete amplifier, right? So the signal is isolated or is being fed into the FET, NMOS FET, using a coupling capacitor. Similarly, the output comes out through another coupling capacitor, CC2. So CC1 and CC2 are coupling capacitors. CS is a bypass capacitor. So this, for bias signals or bias voltages, this, which is DC, this is an open circuit. When AC signals are being considered, this is a short circuit. So the bias values don't affect the AC signal response. Similarly, coupling capacitors at DC, they are open. So only this portion is used for biasing, this portion of the circuit. But once you attach signals, then the signals can come through, and by superimposition, right, we know that superposition tells us that as long as you are in the linear range of the amplifier, the device operates as if the bias and the signal can be just simply added arithmetically, right? So we've studied that when we studied biasing and all that. Okay, so now we need to determine the effect of all the capacitances on the gain, which is V out by V signal of the CS amplifier. So how do we do? We have three capacitors. How do we find the impact or the effect of all these capacitances? Now we know that we can write, for example, the output Vg, which is somewhere here, as the input signal times some voltage divider type formula, right? So for a simple RC circuit, as I've shown you, you can write it in this form, right? So there is the S by S plus um, RC, which is, or 1 by RC, right? And the RC is the sum of these two R's, RG and R signal, times the C. So you are just looking at this circuit in isolation and trying to, you kind of assume that these don't exist, and you're trying to find the effect of just this portion. And so the voltage divider formula, as he shows in the textbook, the derivation is in the textbook, I'm just giving you the final answer. So Vg can be written as V signal times Rg by Rg plus R signal times S by S plus 1 by Rc. So this is similar to this, right? Sorry. Yeah, it's in this form, right? You have an input signal, you have capacitance, then you have this resistance. So your output or your transfer function has this form, S by S plus omega C. So similarly, coming back to our slide, the output by input, of course there is this constant factor, but otherwise it has this S by S plus 1 by RC. So this portion, the 1 by RC, if you designate it as the break frequency, like omega 0, then there are 3 omegas here, so we call this omega P1 or pole 1, which is omega 0, which is just this portion. So I showed you the standard form and I showed you our form here, and you can see from there you can come up with a value of this break frequency due to this CC1 as this. Now this resistance Rg plus R signal is sometimes described in the textbooks as resistance seen by this capacitor CC1 when this V signal doesn't exist and these other don't exist, other capacitances. Then this is the resistance that accompanies this capacitor. So this gives us one break frequency. Similarly, the next capacitor, the CS, gives us another break frequency, which you can see as derived in the textbook using some voltage current divider methods. It comes out to be in this form, and so the next break frequency is Gm by Cs. Now Gm, is transconductance, which is 1 by resistance. So if you assume Gm to be 1 by R, then we have 1 by RCS. So that is another break frequency because of Cs. Now one other formula there is, if there is a source resistance. Here we don't see a source resistance, just a current source is shown, but sometimes you'll have a resistive circuit in the source with Rs. Then the formula modifies a little, but nevertheless the form of this break frequency is just 1 by Rc again, right? Lastly, we have the effect of Cc2, which has its own form, and so this portion I've shown you is the break frequency due to Cc2, which is omega P3, which is 1 by this portion, 1 by Cc2 into Rd plus Rl. So the bottom line is we have 3 capacitors, and each of them gives us a different break frequency. Which is the most important break frequency? That's the question, right? Now, if you combine the effect of all this and all this derivation can be a little tough to follow, but nevertheless you can see that the V output by V signal, which is the overall gain, can be written in terms of the AM, which is the mid band gain, which is assuming no resistance, no capacitances existed at all, meaning they all were zero impedance. Then that gain is called mid band gain, and the other and the effect of the three capacitances then can be shown as a simple product in this form. Okay. Now, luckily, we are not yet doing a whole lot of analysis on exact frequencies, at least in this initial portion. Maybe you'll do it in another course. But for now, our interest is two things. First, we need to know at which point does the 3 dB happen, the drop of 3 dB. And that happens generally at FP2. Now, this Fp and omega p are the same thing, right? They're connected by the factor of 2 pi. F is in hertz, omega is in radians. So, generally, the Fp2, or the highest point, highest frequency where the minus 3 dB happens, that is either because of the source resistance or the source capacitance, this capacitance Cs, or if it is a BJT, then it is CE, which is the emitter capacitance. Okay. So this is a board plot, and what you'll see is there are three sections. First, because of one capacitance, which is Cs, then because of CC2, then because of CC1. That means the lowest frequency is because of the CC1. And because they add to each other, the slope gets steeper, 20 and then 20 plus 20, then 40 plus 20. But we are most interested in this point because from there on we say the amplifier is no good. That means less than this point, it can be 100 hertz or 50 hertz. Less than that, we can say that we cannot trust the amplifier. It won't deliver the performance we need, right? So there are some conditions, but if the highest frequency pole, that means this pole, if that pole, which is actually this pole, the one in the middle, W omega P2 or FP2, if that is higher and it's separated by these two by a factor of 4, so it has to be at least 4 times this, then we can use the simple approximation that FL, which is the 3 dB frequency, is nothing but FP2. Okay. All right. So we have some problems we'll come back and do. I'll also introduce you to BJT, low frequency response. It is pretty much identical to what we just studied for the MOSFET low frequency response. Here also we have three capacitors, CC1, CC2, and then the CE, which bypasses the bias circuit in the emitter for a BJT. This is an NPN transistor. So the three pole frequencies or pole points or break frequencies are omega P1, which is CC1 times the resistance, then omega P2, which is because of the emitter capacitor, this one, that also has the RC form. This whole thing is just a resistance and a capacitance, RC 1 by RC. Similarly, effect of CC2, which is this, is omega P3, another 1 by RC, C is this, R is this. Okay. So basically this R in plus R signal, right? That is the capacitance that is the resistance that this capacitor sees. So you put that as the product in each case. So using these three and similar ideas, the mid-band gain has a formula. And the overall gain has a formula, and the three sections of the board plot are shown here. and the 3 dB point is also shown as FL, and it's generally approximately equal to FP2 if the condition is met. So sometimes this FL can be derived using this formula also. The three RCs are added together. Okay. All right, and then we have some examples that we will do when we come back. Okay. So that is your basic introduction to low frequency response of the CS and CE amplifiers. Okay. All right, when I come back, we'll do some problems on this material.